Hello. In this video, I'll talk about how to prove biconditional statements, and in particular, we'll use proof by contrapositive as part of a proof of a biconditional. We'll also look at a couple examples of this. In particular, we'll prove this result 3.23, and we'll prove theorem 3.24. Let's get started. So, proof of a biconditional. So what I mean by this is proving a statement that looks like, for all x in S, P of x, if and only if Q of x. Remember, this guy means if and only if Q of x. So remember first what a biconditional means. P of x, if and only if Q of x. This has the two directions to it. So this is equivalent to showing that P of x implies Q of x, and Q of x implies P of x. So when we're proving this statement, we need to prove both. Prove both directions. I'll usually phrase this as the direction of an implication. Prove both directions. So we'll actually have two statements to prove whenever we're proving a biconditional. So why am I mentioning this now in the proof by contrapositive section? Well, usually, or I guess a lot of the time, one of these statements, as we've seen, sometimes implications, it works better to prove those by contrapositive. So one of these might be easier to prove by contrapositive than the other, or maybe both of them are easier to prove by contrapositive. So the idea is that one or more of these, one or two of these, is easier to prove by contrapositive than directly. And so that's the idea. We'll prove one statement by contrapositive and the other one directly. Or maybe we'll prove both of them by contrapositive. It depends on the statement. So let's go ahead and take a look at an example of this, and we'll see, what our strategy will be. So result 3.23, here we have n is an integer. We want to show that if 3n, we want to show that 3n plus 8 is odd if and only if n is odd. So if I say let p of n be 3n plus 8 is odd, and q of n be n is odd, then what we're looking at proving here is for all integers n, p of n if and only if q of n. P of n if and only if q of n. And so we have two things to show here, right? We need to show p of n implies q of n, and let me make my arrow go somewhere else. We have to show that. And I'll usually, to indicate that I'm showing the forward direction, I'll just draw in quotation marks a forward implication arrow like this. And to show the backwards direction, I'll indicate a backwards arrow like this. And so here would be showing q of n implies p of n. So we have to prove both of these statements. So that is, in this first case, the forward direction would be showing that if 3n plus 8 is odd, then n is odd. That's the forward direction. And the backwards direction, I would be showing if n is odd, then 3n plus 8 is odd. If I can show both of these two things, then I'll have succeeded in proving this biconditional statement. So I have these two implications to show now. Let's think for a second about how I'm going to do this. I need to come up with a strategy for both. Well, in this second one, if n is odd, then 3n plus 8 is odd, the backwards direction, I'll be able to assume that n is odd. And so I'll be able to write n equals 2k plus 1, and then I'll be able to plug that into 3n plus 8 and hopefully show that that's also odd. So I should be able to do this one directly. So this is my strategy. I'm going to prove the backwards direction directly, and the forwards direction, well, here my assumption would be 3n plus 8 is odd. And if I assume that's odd, I'd have 3n plus 8 equals 2k plus 1. This is like in that last video. This doesn't really respond very nicely to a direct proof. So I'm going to prove this one by contrapositive. Prove this guy by contrapositive. And so what will I actually be showing here? I'll be showing that, so let me type this. So contrapositive would be if n is not odd, if n is even, then 3n plus 8 is not odd, is even. So that's my proof technique. This guy directly, n is odd implies 3n plus 8 is odd, and this forward direction by contrapositive, if n is even, then 3n plus 8 is even. So proof, let's do it. Now we have our strategy down, let's actually do it. So let's say, I'll just say forward direction by contrapositive. And it's okay, and it's actually a good habit to get into, at least in this class, to indicate what proof technique you're going to be using by contrapositive. So assume n is even. Then n equals 2k for some integer k. So 3n plus 8 equals 3 times 2k plus 8. So that's 6k plus 8. And I can factor a 2 out of that. So that's 2 times 3k plus 4. And so I've succeeded in writing 3n plus 8 as twice another integer. And so I'll say hence 3n plus 8 is even. Cool. We just showed the forward direction of this biconditional. Showed that if 3n plus 8 is even, we showed that if 3n plus 8 is odd, then n is odd. We did so by contrapositive. Now the backwards direction I mentioned, we're going to do this directly. So the backwards direction again was if n is odd, then 3n plus 8 is odd. So here we'll assume n is odd. Well, that means I can write n as 2k plus 1 for some integer k. So what do I want to do? 3n plus 8 again, right? I want to show 3n plus 8 is odd. So 3n plus 8 looks like 3 times 2k plus 1 plus 8. This is 6k plus 3 plus 8, so that's 6k plus 11. I want to show this is odd. So what I can do here to show this is odd is I can write this as 6k plus 10 plus 1, something like that. And then I can factor a 2 out of this first one, 2 times 3k plus 5 plus 1. So now I've written it as twice some integer, right? This guy is an integer, plus 1. So that's the definition of a integer being odd. So I can say hence 3n plus 8 is odd. So, okay, summarizing again, we showed the forward direction by contrapositive. We showed the backwards direction directly. We succeeded in showing both of those directions. And so now the biconditional is proved. 3n plus 8 is even, or 3n plus 8 is odd, if and only if n is odd. Notice this biconditional could have been stated a different way. When you think about the contrapositive of a biconditional, it doesn't really matter which order you write it in. I could have wrote this as n is odd if and only if 3n plus 8 is odd. I also could have stated this with the contrapositive instead. That is, p of n if and only if q of n is actually equivalent to not p of n if and only if, sorry, I meant to say equivalent to not q of n. So that would have been read n is even if and only if 3n plus 8 is even. That's okay. These two things are equivalent. If you're not convinced, look at a truth table. All right, so that was result 3.23. Let's do one more result of this type using, doing a biconditional proof of a biconditional using a contrapositive. And that's this one, theorem 3.24. So notice a lot of the things we've proven already are results. We reserve the term theorem for results that are of particular interest. So this one is particularly interesting because we know, n squared is even if and only if n is even. This is something we'll use in the future. And so here we're stating this as a theorem. It doesn't really matter. It doesn't really change it at all if we call it a result or a theorem, but how this book works is the really important ones, the ones we're going to use over and over again, we're going to call those theorems. But there's really no difference between a result and a theorem. All right, so let's analyze this. So here we have n as an integer. If n squared is even, or n squared is even if and only if n is even, so maybe I let p of n be n squared is even. By the way, you don't have to break these down like this. You should, when you're starting out like this, and I'm doing it to illustrate exactly what our proof strategies are going to be, but as you do this more and more, you'll kind of be able to do this in your head before you start to prove something. Think about the statement and its contrapositive, which one's going to be easier to prove, things like this. You should eventually, once you've done enough practice, be able to kind of do this in your head. So you don't have to write this out, but I'm just illustrating it. So what we're proving here is that for all integers n, p of n, if and only if q of n. So again, we have two things to prove. P of n implies q of n, and q of n implies p of n. So let's analyze both of these statements and identify if we should use contrapositive for one or both of them. So p of n implies q of n. This would be n squared is even if n squared is even, sorry. If n squared is even, then n is even. So what do you think? Directly or by contrapositive? Let you think about that while I write this next one. Q of n implies p of n. This is the backwards direction. This would be n is even. So if n is even, then n squared is even. Think about that one. Will we do that directly or by contrapositive? So this is the backwards direction. This is the forwards direction. So in this case, our starting assumption would be n squared is even. So if we assumed n squared was even, we would write n equals to 2k, and we would want to show n is even. So we'd want to show n is twice some other integer. So this starting assumption, n squared equals 2k, is really no good. We could get a hold of n by taking a square root, n equals square root of 2k, and I want to show n is even. Well, how would this imply that n is even? It really doesn't. It's not even clear that this would be an integer anymore, or even rational. So that root directly is no good. Directly is junk. We don't want to do that. But contrapositive, we would show if n is odd, then n squared is odd. Now that seems like something we can do. So that's going to be our strategy, is to do this one by contrapositive. The backwards direction here, we would get to assume n is even, n equals 2k. We could square it, we'd get 4k squared. We can factor a 2 out of that. So we'll do this one directly. So again, let's prove this. Proof. And again, I'll indicate here forward direction by contrapositive. So here I'll assume n is odd, then n equals 2k plus 1 for some integer k. So n squared would be 2k plus 1 squared. All right, that's 2k plus 1 times 2k plus 1. So that's 4k squared plus 4k plus 1. Remember to FOIL this. It's not 4k squared plus 1. And now I want to write this and show that it's odd. So I assumed n is odd. I just found the square of n, and I want to show that is odd. So I'm going to factor a 2. Notice I can factor a 2 out of these two terms, and then I'll be left with a plus 1, and I can show that it's odd. So this is 2 times 2k squared plus 2k plus 1. And so now I have n squared written as twice another integer plus 1. So I can say, hence, n squared is odd. Cool, that's the forward direction. All done with that. Let's prove the backwards direction, and we're going to do this one directly. So let's remind ourselves what the backward direction was. If n is even, then n squared is even. So we'll assume n is even, and that means that n is equal to 2k for some integer k. So n squared, trying to show that's even, is 4k squared. If I square 2k, I get 4k squared. And I can easily factor a 2 out of that. That's 2k squared. So I'll say hence, n squared is even. So forward direction by contrapositive, got that. Backwards direction directly, got that. All done. So it's important, this is a common mistake I see in this class, is especially later on, after we've already talked about this and a couple weeks have passed, people seem to forget that when we have a biconditional statement like this, if and only if, that we need to show two different directions. We have to actually prove two implications hold. So try and remember that. When you see if and only if, you need to prove two different statements, the forward direction and the backwards direction. Oftentimes one of these is easier to prove by contrapositive than directly, and then follow through on it. All right. That's the end of this video. I will see you next time.